Welcome to this lecture series in real analysis. In this lecture, we'll discuss the notion of convexity of a function, which is a fundamental notion in mathematics. In this lecture, we'll see only a small aspect of it. And the main thing that we need to follow today's lecture is Lagrange's mean value theorem. And I'm sure you know this statement by the back of your hand by now. All right. So what is a convex function? Here is the idea, here is the geometric or visual way to look at convexity. So suppose I make the graph of a function and think of this function as defined from reals to reals, even though the domain necessarily doesn't have to be reals, it could be just an open interval or even a closed interval. So suppose you have the graph of a function. We will say that the function is convex if the graph has the following property. Whenever you pick 2 points in the domain and draw these vertical lines, so you're kind of only focusing on this part, and you join the line segments, you join the points on the graph corresponding to the 2 points you chose, you get a line segment. So if we join, we get a line segment. And suppose we find that the graph always lies below the line segment. Then we declare that the function is convex. So once again, we say that the function is convex if whenever we pick 2 points in the domain, we consider the corresponding points on the graph, join the line segment, and find that the graph of the function is always below the line segment that we just drew, we will declare that the function is convex. Okay? So no matter what 2 points you make, no matter what 2 points on the graph you pick and join the line segment, you find that the graph of the function is always below the line segment that you drew, basically that. So it's a very simple idea. And let's first capture this idea formally in the form of a definition, and then see some, and then prove a criterion to decide convexity. I mean, it's not something so easy to, at least on the face of it, it's not so clear as to how to decide if a given function is convex, but there is a very simple criterion. And then we will see some very interesting applications. Okay, so fix some interval. It could be a closed interval, open interval, one side open, one side closed, whatever, but an interval. And to be a little concrete, you can think of this as an open interval. That's good enough. So suppose we have an interval and a function defined on it. We say that the function is convex if whenever lambda is chosen in this range, meaning between 0 and 1, we have this inequality, which is the value of the function. Yeah, so whenever lambda in this range and x and y are in the domain, we have that the value of the function at this point, which I will talk about in terms of the graph, but yeah, so the value of the function at this point is at most this number. Something has been written, but let's try to understand how this captures what we just said in terms of this picture. So suppose you take lambda as half. So then what does this become? This is just saying for lambda is equal to half. This is just saying that the value of the function at the midpoint is at most the midpoint of the values, so to say. And how does this translate in the picture? Suppose this is x and that is y. Then the midpoint of x and y will be somewhere here, x plus y by 2. And this is the value of the function at the midpoint. This is nothing but this vertical height, right? So this vertical height we are saying is at most this vertical height, this whole thing. Right? Because this is fx, that is fy, And if this is the midpoint between x and y, by basic high school geometry, or you want to use coordinate geometry, you use coordinate geometry, this is nothing but the average of these two numbers, right? And this is nothing but the f of the average of the two numbers x and y, right? So this equation is very easy to interpret in this graph. Similarly, if you had chosen lambda as 1 by 3, let's say, if lambda is 1 by 3, what we would be saying is that f of x by 3 plus 2y by 3 is at most f of x by 3 plus 2/3 of fy. And same thing, this number will be somewhere here, right? It is putting more weight on y, so it is kind of trying to lean towards y. So when lambda were half, it was situated exactly in the middle. But if you kind of increase this part, this point will shift towards y, so it will be somewhere here. And this length would then be the left side, and this length would then be the right side. So I hope you're able to see that this algebraic way of capturing the notion of convexity is a proper one. It does capture our visual intuition. Okay, so that's the definition of a convex function, and then you can ask what is it good for? Why are we defining it? Let's see. But before we get into applications, let's prove one simple strengthening, if you will. So we are saying that suppose we have a function defined on an interval I, then the two statements are equivalent. The first statement is that f is convex. The second is whenever we choose n points in the interval and n numbers between 0 and 1, we have that the value at the convex combination of the xi's, this is called a convex, so wait a second, I forgot to write one thing. Whenever we have this with the property that they sum up to 1, we have that the convex combination of the xi's, so this is what I'm calling the convex combination of the xi. So we have the f of the convex combination of the xi is at most the convex combination of the values of f, right? So this is our small lemma. It's hardly a lemma, but has to be stated and proved. So 2 implies 1 is a very simple deduction. Well, just take n as 2, right? If n is equal to 2, what do we see? We see that whenever you choose 2 points in the interval and you choose lambda 1 and lambda 2 such that they sum up to 1, so which is to say that lambda 1 plus lambda 2 is 1, which is just saying that lambda 2 is 1 minus lambda 1. So then this equation just becomes f of lambda 1 x1 plus 1 minus lambda 1 times x2 is at most lambda 1 f of x1 plus 1 minus lambda 1 times f of x2, and this is exactly the definition of convexity that we gave in the previous page. So for the other direction, it's just a matter of simple induction. So let me prove it for n equals 3, and you can easily generalize. In fact, you can directly prove it by yourself with no difficulty. So we will give the proof only for n equals 3. So take 3 points in the interval and 3 real numbers lambda 1, lambda 2 and lambda 3 in the range 0 and 1 such that they sum up to 1, right? And we want to show, or we know what we want to show. We want to show this, assuming f is convex, of course. We're assuming 1. So we are considering this sum, and we want to exploit the convexity of f. So we will make some adjustments. So we will write the rest of the thing as follows. We will make a little adjustment. Right? All we did was multiply and divide by 1 minus lambda 1, and now you can object, what if lambda 1 is equal to 1? Well, if lambda 1 were equal to 1, then lambda 2 and lambda 3 would then be 0, in which case this inequality would be trivial. So technically I should write that this equation holds only when lambda 1 is different from 1. But anyway, I mean, let's not be too pedantic. Okay, and now here I give you an exercise to show that this thing is actually in the interval. This is in the interval. There's very little to do here because lambda 2 plus lambda 3 is exactly 1 minus lambda 1. Right? So if you consider this ratio and that ratio, they sum up to 1. So all you're doing is you're taking a convex combination of x2 and x3, and a convex combination of x2 and x3 will lie in the interval because the interval is an interval. You know, if you pick 2 points in the interval, everything in between them is also there in the interval by definition. So anyways, just convince yourself that this thing is in the interval. And now we use the convexity of f because we have lambda 1 times something and 1 minus lambda 1 times something, where lambda 1 is in the range 0 to 1. So by convexity of f, we have this is at most lambda 1 f of x1 times 1 minus lambda 1 f of, let me write the remaining thing as follows. Right? And now again apply convexity here. The sum of these two things is 1, and these are positive. That's all. So you can apply convexity one more time and you will get the desired thing. Right? And things cancel out, these things cancel out, and you get what you wanted. So it's a very simple induction. All right, so we have this. So what is the upshot? The upshot is, even though the definition of convexity was insisting only on the convex combination of two things, right? Only 2 points from the interval, it self upgrades to convex combination of multiple things for a very simple inductive reason. Okay, great. So let's see at least some examples of convex functions. So the most simple example would be, well, linear functions. So if you just take, let's say, the identity map, which is a special case of a linear map, but let's not go into what is a linear map. Yeah, so this is a convex function exercise, but let me give you a better example. This is a more, this is a non-trivial example of a convex function. Not that it is hard, it's just that it is non-trivial. Pictorially, it should be very clear that it is convex, because once you draw the graph of x square, it looks something like this. Something of that sort. I don't think this is very accurate, but not far away from reality. So clearly it is a convex function, because if you choose 2 points on the graph and draw the line segment, the rest of the, the graph is bounded by your line segment. So the graph remains below the line segment. I mean, that is what convexity is all about, but we need to prove it. So let's try to give a proof of it. So choose 2 points x and y in the domain, which is as big an interval as one gets, and also choose lambda and mu. Let's choose lambda and mu such that they sum up to 1. Yeah, and we want to show this. But what is this? What is the left hand side? The left hand side is, or maybe let's run with both the sides simultaneously. So the left side is just lambda x plus mu y whole squared, and the right side is this, where we have to remember that this equation holds. So this is what we want to show, but let's expand out to the left side. So that's equivalent to showing this. And now what do we do? Yeah, so that is equivalent to showing 2 lambda mu xy is less than equal to lambda x square minus lambda square x square plus mu y square minus mu square y square. All I did was take this stuff to the other side. Here let me make an adjustment. Let's just pull out x square and lambda at the same time. So we get lambda times 1 minus lambda x square. And here we do the same trickery, or not really trickery, but whatever. Right, I kind of skipped one step or meshed them in one. Anyway, but what is 1 minus lambda? 1 minus lambda is mu. Let me not mesh it here itself. So lambda times mu x square plus mu times lambda, which is same as lambda times mu, times y square. All I'm using is that 1 minus lambda is mu and 1 minus mu is lambda. Okay, so we have lambda mu coming as common. Right, this is what we want to show. Now, if any of lambda or mu were 0, this inequality would be trivial. So in that case, we were already done. So assume that both are non-zero, in which case we can cancel out lambda mu, and therefore we are just required to show that 2xy is at most x square plus y square. Just give me 1 second. So let me write it here. So that is, we want to show 2xy is at most x square plus y square, but that is true. Right? This is clear because x minus y whole square is non-negative, and if you just expand it out, you get that. So the square function is convex, and as a consequence, we get this very nice inequality, that if you choose n real numbers, we have this inequality. Now, why is that? The reason is very simple. The reason is we take the n numbers, all of them equal to 1 upon n. Clearly, each of them is between 0 and 1, and all of them add up to 1. So just by using this equation, by convexity of f, we know that this holds, as we proved in the previous slide. We know this holds, and if you just substitute these values and instead of f write square of the argument, this is exactly what you see. Proving this directly is a little bit of work, not a lot of work, but a little bit of work, and it may not be immediately obvious. But it's a beautiful inequality. And there's one more thing I want to say here. Yeah, so this is a second example. So here I want to say that this function is not convex. This function is not convex. Well, I'll leave the details as an exercise, but if you just draw the graph of this function, the graph of this function looks something like this. Something like that. And clearly, if you choose these 2 points, let's say 1 and -1, the line segment that you get corresponding to them does not have this property that it lies above the graph of the function. Right? It intersects the graph at 0 and goes below it on the left side and goes above on the right side. So it violates the convexity property. You can prove this formally by writing it out, whatever is clear from the picture. So this is an example of a non-convex function. Okay, great. Here is a simple exercise that the sum of two convex functions is convex. So this is an exercise. Then we have the fact that the product of two convex functions may not be convex. Okay. So this one can see from an example. I mean, one can construct many examples, but here is one. So I'll leave the details to you, but just consider the function f as fx equals x for all x, and consider g as gx equals x square for all x. Then f and g are both convex, but f times g is not convex. So let me just leave it here. Let me not write anything. Anyway, my iPad is misbehaving today. So f is convex, g is convex, but their product is the cubing function, which is not convex. We've already commented on that in the previous page. Okay, wonderful. But here is one more thing I want to say. I don't know if I have already said it in the next slide, but no harm in saying it here. This function is convex. If you have your domain as all of the reals, then this description wouldn't give a convex function, as we saw. But if you restrict the domain to only the positive reals, then you do get a convex function. You can also include 0, no harm in that, but let's leave it like this. And again, if you draw the graph, it looks something like that, and that is certainly convex. You can again formally prove it. But we will soon see a criterion which will immediately show the convexity of it. We don't need to do any work really. All right, let's proceed. So here is the criterion. This is the main theorem of this lecture. So suppose we have a function defined on an interval which is twice differentiable, meaning you can take its derivative and you can also take the derivative of its derivative. It is differentiable 2 times such that the second derivative is always non-negative. Then the function is convex. So here we are assuming that the function is defined on an open interval. If you want to have a corresponding theorem for closed interval, perhaps you would have to, I think even then this hypothesis would suffice, no problem there. Yeah, but let's keep things simple. Let's be content with open intervals. So this helps us prove convexity very easily. For example, if you had the squaring function, if f was this function, then clearly it's convex if you use this criterion. If you differentiate f 2 times, you get the constant function 2, which clearly satisfies this inequality. So it definitely helps. Okay. So choose 2 points, x0 and y0, in the domain of f, right? And also let lambda be in this range. Want to show that f of lambda x0 plus, I'll write mu y0, where mu is 1 minus lambda. This is at most lambda f of x0 plus mu f of y0. And it will be convenient to assume, without loss of generality, that x0 is strictly less than y0. That we can assume without loss of generality. Let me draw a picture, even though that is not very important here. So we have x0 somewhere here and y0 there, right? And once we show this, we will have shown convexity. So there would be many ways of doing such a thing, but here is one way. So define capital F from this closed interval to real numbers as f of t is this difference. Right? And the blue thing can be rewritten now as this statement that we want to show that f of y0 is non-negative. That's just an immediate translation of that statement in the language of this in this function capital F. Okay, and that is what we will achieve by using Lagrange's mean value theorem. So first we will compute the derivative of capital F, but before that let's just note one thing. So note f of x0 is 0. Alright, and now let's compute the derivative of capital F, and that is nothing but this thing minus that thing. Immediately from chain rule, we can take mu outside, right? And now here we can use Lagrange. So t is somewhere between x0 and y0, right? T is chosen from this interval, so t is somewhere between x0 and y0. Say it's here, and this number is between x0 and t, right? So it's somewhere there, and therefore by Lagrange, what is this difference? This difference is f double prime at z, where z is somewhere between these two things, right? So z is somewhere there, and that times this difference. But this is a non-negative number. In fact, yeah, let me just leave it at that. This is a non-negative number because of what I just said here. T minus that is going to be non-negative, right? This is between x0 and t, and therefore this is non-negative. This is anyway non-negative by hypothesis. Mu is also non-negative, so this is non-negative. So now we just combine this observation along with this observation to deduce that f of y0 is indeed non-negative, right? Since y0 is strictly greater than x0, and since the derivative of f is always non-negative, f is an increasing function, and since f of x0 is 0 at x0, the increasing nature of f now implies that that the function f has to be non-negative at y0, and that is what we wanted to do. So that shows the convexity of the function little f. All right, and now let us see some applications of what we just proved. So suppose we have an even integer, and we define the function little f as the kth power map. K is an even integer, and f of x is x to the k for all x. Then f is convex. Reason is very simple. We just use the criterion just proved. We have f double prime x is k times k minus 1 times x to the k minus 2. And since k was even, this is also even, and hence this is non-negative. This is anyway non-negative because k would be at least 2. So this is non-negative, and that's it. So that proves that the kth power map is convex, and as a consequence if you have an even positive integer k, then for any n real numbers, we have this equation. Sorry, not equation, inequality. This is what we stated for k equals 2 earlier, but now we can say it for general k. In fact, we can say a lot more than this. All we need is just to take some convex combination of x1 up to xn, but here we have taken the simplest one. Anyway, so we have this, and here is an exercise for you. If you have an odd integer, doesn't matter, it could even be negative, then this function defined this way, again the kth power map, for all positive x this time, the domain is only the positive x's, we claim that f is convex. Just apply the criterion, you'll get it. And you can prove these kinds of inequalities now. I leave that to you. Yeah, I think that's it. So just try to see what is the, what are the applications of this thing, and you can experiment, like you can construct your own convex functions and write down such inequalities. Much more complicated ones, in fact. Alright, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.